Hi, my name is Johan Kristiansson and I'm a senior researcher at RISE, Research Institutes of Sweden. I'm also working at EuroCC National Competence Center Sweden, ENCCS, funded by the EuroHPT joint undertaking. ENCCS and RISE provide resources and expertise to support research and innovation in the industry, public sector and academia. In this video, I will demonstrate how to use ColonyOS on ICE Connect, a cloud service provided by RISE. This screenshot shows the ICE Connect portal, where various services like OpenNebula and S3 are available. In this video, however, I will focus on the Kubernetes service. I'll walk you through training a machine learning model using the NVIDIA H100 card available within an experimental Kubernetes cluster. But before we dive in, let's first take some time to explain what ColonyOS is. ColonyOS is a meta operating system designed to implement compute continuums. A compute continuum is the next step in the evolution of computing, an integrated seamless collection of computing resources that spans devices, environments, and infrastructure, all accessible through a unified interface. ColonyOS is designed to integrate with various technologies under a unified framework, but rather than managing isolated systems and tools, users can now access and utilize computational resources through a cohesive framework. The ultimate goal of this technology is to make computing as seamless and ubiquitous as electricity. Think about how we use electricity in our home. When you need to power different devices like a vacuum cleaner or kitchen appliances, you simply plug them into a power outlet. If you need to move your vacuum cleaner to another room, you can easily switch to another power outlet to continue cleaning. We want computing to work in a similar way. Suppose you need a supercomputer to train a machine learning model. You can then contact us, and we can help you apply for access to our EuroHPT system, like the Lumi supercomputer. If the application is approved, the Lumi system can seamlessly be connected to your personal continuum. And if you need a public cloud, you can easily connect it too. The same applies if you have a local compute server under your desktop. RISE is also providing a testbed for edge computing, which can be connected to ColonyOS. You can also use ColonyOS to manage and control IoT devices. Users then seamlessly tap into the continuum to get access to computational resources. A common use case is to train machine learning models, but it can also be used to implement services, for example, remote sensing services to process sensor data in underground mines, or process satellite data to implement Earth observation services. And when you don't need a supercomputer anymore, it can simply be detached from ColonyOS or replaced with another platform. This allows users to have the right level of computing power at the right time and place. A colony is a decentralized cloud consisting of loosely connected executors forming a unified compute unit. The demo setup consists of 4 different executors. Executor function as middleware and responsible for connecting different platforms to a colony, for example, Kubernetes, Slurm, or Docker. In the demo, we'll focus on the kube executor, which runs ColonyOS processes as batch of Kubernetes. Users interact with a colony by submitting so-called function specification to a colony server. The function specification is then wrapped into a process and assigned to one of the executors. Now, let's see ColonyOS in action on the ICE Connect platform. So let's first log into the ColonyOS dashboard. In the dashboard, we can, for example, see which executors are currently available. We can also see on a map where they are located. The kube executor is running at the ICE data center in Luleå in northern Sweden. ColonyOS also functions as a ledger, which makes it possible to track and view the entire process execution history. This ensures transparency and accountability, and is particularly useful for debugging and troubleshooting. For example, this process was successful. It was executed by this executor, and we can also fetch the log that was generated when the process ran. Another feature of ColonyOS is workflows. A workflow is a series of processes executed in a specific sequence. Workflows enable integration and coordination of different platforms, for example, combining multiple platforms. Finally, ColonyOS also features a meta file system called Colony File System. Colony File System can be used to transfer data to the continuum, but also transfer data between executors. So let's use the Colony CLI to submit a function specification to launch a new process. So here, this window shows the Rancher dashboard connected to the ICE Cube, which is the experimental Kubernetes cluster we're going to use. The Cube executor is running here also as in a deployment. The Cube executor is connected to a ColonyOS server, Colony server, to get process assignment. And I prepared a very simple function specification. This function specification runs the NVIDIA SMI in a TensorFlow container. And the first part here defines which executor type that should get this kind of assignment. That should be a container executor. And I particularly want to use an executor that has the name ICE Cube. This part defines kind of requirement. In particular, I want to use NVIDIA H100 card. The vault time is particularly important because it prevents failed process to get stuck on Kubernetes forever. So the process will be terminated after 700 seconds if it's not successful. So let's submit this process. So when I submit this process, then this function specification will end up at the Colony servers, and then it will be assigned to the Cube executor, which will actually run the process. And it will run as a batch job on Kubernetes, and we can see the batch job is coming up here. And here is the NVIDIA command. And then the batch job will be automatically removed from Kubernetes after some time. All right. So I want to show you another tool called Pollinator. And Pollinator is a tool that I personally use a lot for training machine learning models. So let's create a new Pollinator project. We can start by creating a new directory called demo. And we can also list which executors are available, and we want to use the ICE Cube executor. Then we will type pollinator new -n ICE Cube. And then it will generate a template, an empty project. This YAML file is very similar to a function specification I previously showed you. For example, here I can specify requirements and which Docker container I want to use to run this job. This is in this case I want to run the command Python, and I want to use this source file called main.py. And you see there's another directory called CFS here, and these directories are automatically synchronized with Colony file system. The source and the data directory are synchronized before the container starts, and the results are synchronized after the container has finished. So this is a way of transferring a result back to my local computer. The source file contains this main.py file, and so we can remove all this code, and we can call it hello world or something like this. Hello world 1, 2, 3. And to run this, I will go back to here, and then I will just type pollinator run run -- follow, and then it will start a new batch job on Kubernetes. And it might take some time to start the pod. In this project YAML file, we also specify that we want to pip install some extra packages before it actually starts, which is very convenient to do, as you don't have to rebuild the container. And here we got hello 1, 2, 3. the result here, and we can also search for logs. Another feature is you can search for logs. Search like hello, and here we can get the ID of the process. So let's look up this process. Colonies process get -p. We can get the information about this execution. For example, it ran for 16 seconds, 17 seconds. We can also get the log if you know the process ID. So now I have prepared a machine learning pollinator project that I will demonstrate how to use and how to train a model using pollinator. So here we have a machine learning pollinator project, and we are going to use an NVIDIA H100 card to train this model. And you can notice here we're going to use IceCube, but we can also use Leonardo Poster HPC system. So the only thing we need to change is to uncomment Leonardo and comment away IceCube to use an HPC system. And then it will run using Slurm and not Kubernetes. So here we have a data set. It's actually satellite images. And so this is the data set we're going to use. And this data directory will be uploaded synchronized with Colony file system. And it will be kept on the Kubernetes volume for efficiency purposes. And then we have the source here. We have the actual model here. It's a quite simple machine learning model to detect water in the satellite images. So it's image. It's a segmentation model, and so we want to run for 10 epochs, which is, we can change this to maybe 3 epochs, and then we will save the final model in the result directory, and it will be called demo 1 to 3, something like that, demo unit. So when this finish, I will have a file name. The model weight will be called demo unit _123, and that will be available in the result directory. So in order to run this, I will just type pollinator run -follow. This might actually take some time to run. So let's wait for a while. And now the model has been trained. So, and the model weight has been synchronized back to our local computer. So if you look in the CFS on the result, the models, we can see that the new model is stored here. I encourage you to collaborate and contribute to ColonyOS. Together we can drive groundbreaking innovation, share knowledge, and shape the future of computing, the future of tomorrow. For more information, please take a look at the following links. Thank you for watching this video.